Good morning. Myself, Dr. D. Sudhakar, working as Professor and Head of Mechanical Department at Siddhartha Institute of Science and Technology, Puttur. Today, I am going to discuss about this thermoelectrical machining process. So, this is the syllabus in thermoelectrical machining process, electrical discharge machining, working principle, equipments, process parameters, material removal rate, tool and power circuits, tool wear, and dielectric flushing. Now we'll discuss about this introduction to electric discharge machining process. This is also abbreviated as a EDM. Whenever sparking takes place between two electrical contacts, a small amount of material is removed from each contact. This fact was realized and the attempt were made to harness and control the spark energy to employ it for its useful purpose, say for machining of metals. Normally in daily life, suppose when two electrical wires, if you take two electrical wires and if you touch with each other, automatically some spark will come. If the spark, with that spark also, a small amount of material is also removed from the each other material. And this is taken, and the same principle we have applied in the machining process also. It was found that the spark of the short duration and high frequency are needed for efficient machining. But in normal electrical short circuit, here also some amount of material is removed from the each material workpiece. But at the same time, if you want to remove more amount of material from the workpiece, you need a spark of short duration and high frequency needed for efficient machining. Further, it was also observed that if the discharge is submerged in dielectric, the energy can be concentrated in a small area. So after that, if you want to remove a small amount of material or exact place from where if you want to remove the metal from the workpiece, if it is conducted within the dielectric, then it will be better, better, and we are going to get the better machining and best surface finish also. A relaxation circuit, that is also called as a RC circuit, is proposed in which the electrodes, that is the tool, is acts as a cathode and workpiece is acts as an anode, are immersed in a dielectric. Those dielectric fluids are like kerosene are connected to the capacitor. The capacitor is charged from the DC current source. Okay. And here the RC circuit also I'm going to explain how the voltage and critical voltage versus time and critical current versus time relationship for the capacitor. So as soon as the potential across the electrodes crosses the breakdown voltage, that is the VB, the spark takes place at a point of least electrical resistance. So whenever you supply the voltage between the two electrodes, that is the tool and workpiece, the in between the tool and workpiece, there is a very small amount of gap is there. Because of that one, initially the arc will not be produced. So after some couple of time, the voltage will reach beyond the breakdown voltage. Whenever this voltage is increases beyond the breakdown voltage, automatically it crosses the insulation media or the dielectric fluid, which is lies in between the tool and workpiece. And wherever it is a very small gap, it is there in between the tool and workpiece, there the sparks will be developed and it is going to move and touch the surface of the workpiece. It is usually occurs at the smallest inter-electrode gap. The inter-electrode gap is the gap in between the tool and workpiece. So whatever the gap we are going to maintaining between the tool and workpiece, that gap is also called as a inter-electrode gap. And after each discharge, capacitor recharges and spark appears at the next narrowest gap. The occurrence of each spark generates heat energy, which is shared in different modes by workpiece, tool, dielectric, debris, and other parts of the system. See, whatever the heat generated, during this electrical discharge machining process, those electrical those heat energy will be distributed to the different parts of the equipment. That is, some amount of energy will be, most of the energy will be transferred to the workpiece, and less amount of heat will be transferred through the tool, and some amount of the heat will be transferred to the dielectric, and some more amount of heat energy is also transferred to the debris which are present in between the tool and workpiece. The dielectric fluid, whatever we using, it serves for the important functions such as cool down the tool and workpiece. Whenever we supply the voltage in between the tool and workpiece, very large amount of heat will be developed. Because of the time, because of the heat, the tool or workpiece may damage. So in order to overcome or in order to reduce the heat generation during this process, for that purpose, we are going to use this dielectric fluid. And also this dielectric fluid is cools the tool and workpiece, and it maintains the strength, stability, and the structure without any problem. And another important function of this dielectric fluid is it cleans the inter-electrode gap and localizes the spark energy into a small cross-sectional area. So during this machining process, whatever the material is removed from the workpiece removed from the workpiece, sometimes it may struck in between the tool and workpiece. So because of that, what will happen? The same amount of material will be removed again and again. So the heat will be supplied to the same material. So in order to overcome that problem, continuously we have to flush away the material is removed from the workpiece. That is also important function of the dielectric fluid. And another important function of the dielectric fluid is whatever the energy is generated during this spark, that energy will be concentrated. It creates to concentrate on specific area on the small cross-sectional area. So the main purpose of this dielectric fluid is to reduce the temperature of the tool and workpiece and to flushes away the material or chips or debris, whatever you remove from the workpiece. And another function is it directs the spark to reach a small cross-sectional area of the workpiece. The energy content in each spark and frequency of spark are governed by the conditions in the inter-electrode gap. So how many quantity of sparks are generating, at what frequency we are going to generating the spark, it is completely depends upon the inter-electrode gap. So this is the schematic diagram of the electrical discharge machining process using relaxation circuit. And this is the workpiece, and this one is the tool. In between the tool and workpiece, we are going to supply this dielectric fluid, and this tool is acts as a cathode, and workpiece is acts as an anode. So this is the tool. This is the minus. That is the negative. Acts as a cathode, and this is the workpiece. It acts as an anode. It indicates the positive sign. So in between the tool and workpiece, this dielectric fluid will be there. Whenever the voltage process this breakdown voltage, automatically this ionized column will be formed, and in between this ionized column a spark will be generated, and that spark will be moved from tool towards the workpiece, and it will be falls on the surface of the workpiece. And because of that spark, very large amount of heat will be generated. Because of that heat, some amount of material removed from the workpiece and melts and evaporation will be takes place. So this is the principle what we are going to use in dielectric machining process. And this is the diagram represents in between the voltage and time. So when the voltage cross in between the breakdown voltage, automatically spark will be developed. Because of that spark, and the material is removed from the workpiece. So this is again the principle in elaborative way. This is the tool holder, and this hatched one is the tool electrode. It acts as a cathode, and the bottom one rectangular piece shape indicates the workpiece, and it acts as a anode, means plus. So in between the tool and workpiece, this dielectric fluid will be flow. So whenever we supply the voltage in between the tool and workpiece, automatically a plasma channel will be developed. In between the plasma channel, okay, this molten spark will be developed. This spark will come in the downward direction and it removes the material from the workpiece, and whatever the material is removed from the workpiece over here, that will be flushed away by this dielectric fluid, and the same shape of the tool will be reproduced on the surface of the workpiece. So this is the diagrammatic representation of the equipments which are using in the electric discharge machining process. So this is the tool. The yellow color rectangular shape bar indicates the tool, and this blue color indicates the workpiece rectangular shape. And then this tool is acts as a cathode, and the workpiece is acts as a anode. And this is a dielectric fluid tank, and this dielectric fluid tank is pumped from tank to the pump. By means of this pump, we are going to pump from dielectric tank to the filter. Here, if any debris or if any unwanted particles are there, it will be filtered properly, and some amount of fluid will be transferred directly into the tank, and some amount of dielectric fluid will be passed through the workpiece. So this is the hollow shaped workpiece. So whenever this dielectric fluid is passed through this tool, and it spread over the surface of the workpiece, and in between the tool and workpiece, because of this high voltage and current, a spark will be developed. Because of that spark, very large amount of material is removed from the workpiece. Means whatever the shape of the tool, the same shape will be reproduced in the workpiece by removing the material from the workpiece. And this is a DC pulse generator. By means of that, we are going to supply to the tool and workpiece. Means here the workpiece is acts as a positive, that is the anode, and a negative current is supplied to this cathode, that is the tool. Now coming to the schematic of the basic EDM processes explained in the previous diagram. In this process, the workpiece and tool are submerged into a non-conducting dielectric fluid, which is separated by a small gap, that is inter-electrode gap for sparking. So the dielectric fluid insulates the workpiece from the tool and creates the resistance of electricity flow between the tool and workpiece. Initially, no spark will be developed in between the tool and workpiece because of the dielectric fluid which is present in between the tool and workpiece. It acts as a insulator. The dielectric fluid may be typical hydrocarbon oil, that is the kerosene oil, or deionized water. It also helps in cooling down the tool and workpiece. So because during this machining process, because of its spark, very large amount of heat will be generated. That heat will be transferred to the tool and workpiece. So if the temperature is more, the tool or workpiece may damage. In order to overcome that problem, this dielectric fluid will absorb the required amount of tool and required amount of heat from the tool and workpiece. That is the one purpose of the dielectric fluid. And another function of this dielectric fluid is it clears the inter-electrode gap. Means whatever the debris or whatever the unwanted particles present in between the tool and workpiece, and it will be removed by supplying this dielectric fluid with high pressure, and it concentrates the spark energy to a small cross-sectional area under the electrode. Means whatever the spark generated from the tool, it will be transferred towards the workpiece, and it should not go away. So this dielectric fluid acts as a channel. It creates the direction. It directs the sparks to touch the surface of the workpiece wherever it's required. Next, as the two electrodes come closer to one another, the dielectric field intensity increases. Means when the tool and workpiece are come closer to each other, when it reaches the minimum inter-electrode gap, automatically the electric field intensity increases beyond the strength of the dielectric and enabling the break, and thereby it allow the current flow between the two electrodes. Means initially there is no spark will be developed because of this dielectric fluid. So whenever this two electrodes, there's a tool and workpiece are come closer to each other, and if it reaches a very small gap, that is the required inter-electrode gap between the tool and workpiece, the intensity of the current will be increases, and because of that one, the insulation will be breakdown, and the sparks, whatever the spark is developed, the spark is developed. As a result of this effect, intense heat gets generated near the zone. So whenever it's the breakdown, the insulation is breakdown, very large amount of heat will be get generated near the zone, which melts and evaporates the material in the sparking zone. So whenever this spark is touches the surface of the workpiece, automatically very large amount of it will be generated, and because of that one, the amount of wherever it touches the surface of the workpiece, there the metal melts and evaporation will be takes place. As the flow of current is momentarily stopped, the some fresh dielectric fluid liquid particles come to the position between inter-electrode gap, which restores the insulating properties of the dielectric field. Here, the on time and off time, pulse on time and pulse off time, these are the two important parameters. So during this pulse on time, the current will be passed. During that time, the spark will be generated, and during the off time, the insulating the dielectric fluid flushed away the used dielectric fluid, and again the new dielectric fluid is coming into the picture in between the tool and workpiece. Again, the insulation will come into the picture. The flushing refers to the addition of new liquid dielectric to the inter-electrode gap. The flushing means the previous liquid, whatever it is there in between the tool and workpiece or in the inter-electrode gap, this dielectric fluid is having very less insulation, so that this dielectric fluid will be flushed away and new dielectric fluid will be come into the picture, and again it restores its insulation. A close view of the EDM process is shown in the previous figure. The spark occurs at spots where the tool and workpiece surfaces are closest, since the spots changes after each spark because of the material, because of the spark travels all over the workpiece. This results in uniform removal of material, hence the exact shape get reproduced on the workpiece. So this is again the diagrammatic representation of these different components in the dielectric fluid, and this blue color rectangular box indicates the DC power supply, and the positive terminal is connected to the workpiece, and the negative terminal is connected to the positive terminal is connected to the workpiece, and negative terminal is connected to the workpiece. So in between, this is the dotted lines. All dotted lines indicates the dielectric fluid, and the dielectric fluid is pumped through the pump and it passes through the filter. Here the unwanted particles will be removed, and again it will be passed through this pipe, and again it will enter into the enter through the tool into the machining zone. Here the material spark will be generated, and because of that spark, the material will be removed from the workpiece. So whatever the shape of the tool, the same shape will be reproduced on the workpiece. The parts of the electrical discharge machining process, the main components includes are DC pulse generator, voltmeter, ammeter, tool, dielectric fluid, pump, filter, servo controlled feed, fixers, and table. Now coming to the first one, there is a DC pulse generator. This is the source of power for machining operation. The DC power is provided. So from means of this DC pulse generator, we are going to supply the DC power which is required for this machining process. The positive terminal is connected to the workpiece, it acts as an anode, and the negative terminal is connected to the tool and it acts as a cathode. Now coming to the voltmeter, we know that the voltmeter is used to measure the voltage. The same device is used for this purpose in order to measure how much amount of voltage we are going to supplying in between the tool and workpiece. Then ammeter, and it is used to measure or checking the current flow. If the ammeter is not connected, we may not able to see how much amount of current is flowing, and whether the flowing of current is there or not also we cannot check. So that we have to use this voltmeter and ammeter to check the voltage and current which is passed through the tool and workpiece. Now coming to the tool is connected to a negative power source, and whereas the workpiece is connected to the positive power source. The fluid flows from the filter to the tool for the operation. When the power supply is increased, a spark is generated between the tool and workpiece and the machining begins. The dielectric fluid, and it has an insulation property. In the dielectric fluid may be like deionized water or kerosene oil, kerosene, or some other edible oils can also be used as a dielectric fluid. And we all know that what is meant by insulation also be, because of the insulation, the power, the current will not be passed, or voltage and current will not cross from tool to the workpiece until it reaches the breakdown voltage. The insulation means that no current flows from one component to the another component. So when the power supply is turned off, means during the pulse of time, the dielectric fluid will be ionized in the form of an ion, which will help between the tool and the workpiece again. Now another point is the pump. The pump is connected there to transport or to supply the fluid to the filter. There the filter will remove the unwanted materials or debris from the dielectric fluid, and the cleaned dielectric fluid again it will pump to the machining zone. Now coming to the filter, as the name implies, this used to filter out the various particles, such as if dust particles are present in this device, or the filter will remove them and then send them to the tool operation. Next, servo controlled field. The main purpose of this servo controlled mechanism is to maintain the constant inter-electrode gap between the tool and workpiece. So this servo controlled mechanism will detect the gap between the tool and workpiece, and accordingly it moves in the downward direction in order to maintain the constant inter-electrode gap. If the inter-electrode gap is not constant, or if it is more, then automatically the material removal rate will be reduced. So that we have to maintain constant. We have to maintain a constant inter-electrode gap between the tool and workpiece. Next one is the fixers, and these fixers are used for holding the table. On the table, we are going to place the workpiece. Next, table, and these tables is used for holding the workpiece properly without moving during the machining process. Now coming to the input parameters. What exactly we are going to monitor or we are going to give in electrical discharge machining process. That is the current, spark voltage, spark frequency, and inter-electrode gap. And we will see how it is going to affect on output responses like metal removal rate, surface finish, dimensional accuracy. So here showing that as the current is increases, okay, what will happen? The MRR, metal removal rate, as well as increased value of surface roughness. Similar effect is also observed when the spark voltage or breakdown voltage is increased. Means that when the current is increased, means very large amount of heat will be generated. See here, see this diagram. This is the 1 amp, this is the 2, and this is the workpiece. Bottom one is the workpiece, and this is the spark. This is the 1 amp, this is the 2 amp. See the number of amps is increases, means current is increases from 1 amp to the 2 amps. Automatically, the metal removal rate will be increased from here to here. See here the amount of material is removed from the workpiece here is somewhat small because of the 1 amp. But here 2 amps, 3 amps, 4 amps, automatically the spark intensity will be increases. Because of the spark intensity, very large amount of heat will be generated, and because of that heat, very large amount of material removed from the workpiece. So by means of this, the this we can understood this as the current is increases, automatically the metal removal rate will also increases. And again, when the spark voltage is also increases, the metal removal rate will also be increases. However, an increase in spark frequency results in improved surface finish. See here, this is the 10 amps. Here also 10 amps, but here the current is same and the voltage is different. Because of the high voltage, the number of sparks here 1 arc, is the 2 arcs, is the 4 arcs. Here the number of arcs means the spark frequency is increased. Whenever the spark frequency is increases, each spark will remove the very small amount of material is removed from the workpiece. Whenever it removes the small amount of material removed from the workpiece, we are going to get very good surface finish. Now see this diagram. What is the effect of pulse duration on metal removal rate? And during the at 20 microseconds, the metal removal rate per 4.5 amps. This is the metal removal rate. Okay. If the Kisan pulse duration is increases, the metal removal rate will be decreases. For this is the 4.5 amps, this is the 7.5 amps, this is the again. This depends upon the electrode material. The circular triangular shape line indicates the brass and circular shape line graph indicates for copper tool, and this black color circle indicates the copper tool. So whenever the tool and current is also changes, accordingly the metal removal rate is also changed. Now coming to the pulse duration versus surface roughness, means when the pulse duration is increases, the surface roughness is also increased. See the graphs, automatically it is in somewhat increasing automatically. Because of that one, the surface roughness is increased. And here we have tested for the brass and copper tools. Now coming to the electrodes. See here we are going to using two electrodes. There is the tool and workpiece, and these two equipments are acts as electrodes. However, in general, the word electrode is used only for tool. The material, but in this electric discharge machining process, we are going to consider about the only tool. We are not going to bother about the workpiece. The material to be used as a tool electrode should possess the desirable properties like easily machinable, low wear rate, good conducting capacity of electricity, and it should be good conductor of heat, cheap and readily available. So this is when we are going to selecting for the manufacturing of this tool in this electrical discharge machining process, we have to remind some points. The important desirable properties are like it should be easily machinable. Suppose if you want to prepare a complicated profile on the surface of the workpiece, then we have to prepare a complex shape of the tool. If the tool material is easily machinable, then we can manufacturing a tool with complex shape also, and it should have low wear rate, and it should be good conductor of electricity, and it should be a good conductor of heat, and it must be available in cheap, and it is readily available in the market also. For example, graphite. Say if you take the graphite, the desirable properties are like easily machinable and low wear rate and high conductivity. That is the good. And then copper, brass. And these two materials, if you use these materials as a tool material, and they are highly stable and relatively low wear rate. And if you use the copper tungsten, the desirable is having a properties like low wear rate, but it's somewhat expensive in comparison to the previous materials, and it cannot be easily shaped. So copper tungsten material is having some limitations. Suppose cast aluminum, copper boron, and silver tungsten are some of the materials that are used for making of the tools in electrical discharge machining process. However, copper and graphite are more commonly used because they can be easily machined. A graphite electrode with finer grains results in lower tool wear rate. So that is the important part. This is here in electrical discharge machining process, the preparation of the tool is somewhat time taking process and somewhat costly process. So if the tool wear rate is low, then automatically it will fetch and it will advantage for us. So there is no need to change the tool frequently. And it is also gives better surface finish and higher MRR. So low tool wear rate and better surface finish and higher MRR. So this is the thing what we expecting in any machining process also. However, its brittleness is an undesirable characteristic because of which it is prone to breakage. But in spite of these advantages, it's having one limitation also. That the limitation is the brittleness. Because of that one, sometimes it may break. So this is the power circuit. So what we're using in the electrical discharge machining process, and here the DC voltage source. Okay, and this is the RC circuit, and it is the negative terminal is connected to the tool. It acts as a cathode and it moves in the downward direction and upward direction based on the instructions given by the servo controlled mechanism. And this is the box. Here in that one, we are going to place the dielectric fluid. On that one, we are going to place this workpiece, and the positive terminal is connected to the workpiece, and it is acts as a anode. See, this is the charging circuit and this is the discharging circuit. During the pulse on time, the uh, machining will be takes place, and during the discharging time, during the discharging circuit, because during this time machining will be takes place, and during the charging time again the charging will be takes place. Here we are going to discuss about the tool wear. An increase in power pulse duration decreases the relative electrode wear. So the pulse duration increases. The increase in pulse duration, suppose from 20 microseconds, 50 microseconds, 100 microseconds, 200 microseconds, and 500 microseconds. Here it is increasing. See, we are taking the pulse duration in microseconds on the x-axis, and relative tool wear rate we are going to taking on the y-axis. Means when the pulse on time is increases, because of that one, it gives sufficient amount of time to discharge the current towards the workpiece, so that what will happen? The electrode wear will be less. Now that we are going to discuss about the dielectric system. It consists of dielectric fluid, the reservoir, filters, pump, and delivery devices. A good dielectric fluid should possess certain properties. Examples like it have high dielectric strength, that is, it remain electrically non-conductive until the required breakdown voltage between the tool and electrode is attained. That is one. Then second one is it should take the minimum possible time to break down once the breakdown voltage is reached. Means ignition delay time should be less. Next, deionize the gap immediately after the spark has occurred. Once the spark has occurred, it should deionize immediately. Because of that one, very large amount of it will be generated, and because of that one, the material will be removed from the workpiece. And another function is it serves as an effective cooling media. Means whatever the heat generated during this machining process, it should transfer properly through the various component, and it should carry away maximum amount of heat. And last point is the last function is it should have high degree of fluidity. Means it should flow easily in between the tool and workpiece onto the reservoir and through the dielectric pump, filters, and again it will come back to the machining zone. The fluids commonly used as dielectric fluids are transformer oil, paraffin oil, kerosene oil, lubricating oils, and deionized water. Suppose if you take this deionized water, it gives high metal removal rate and the functions as more effective cooling medium, but also causes high electrode wear rates. Now coming to the further, it suffers from the drawback of causing the corrosion. As it is a water, it is going to give some problems related to the corrosion. To overcome these problems, inhibitors are used, but they result in increased electrical conductivity to an unacceptable level. So if you want to overcome the problem of this rust formation, we are going to use these inhibitors. But the addition of inhibitors to this dielectric fluid, what will happen? The electrical conductivity will be increases and it will be reaches to the unacceptable level. So that the deionized water is commonly used as dielectric fluid in wire EDM also and drilling of small diameter holes. Now coming to the filtration of dielectric fluid before recirculation is highly essential. Means before supplying the dielectric fluid into the machining zone, the filtration is very much important. So whatever the debris removed from the workpiece, those debris must be flushed away and it carries away by this dielectric fluid. Means whatever the debris present in this dielectric fluid must be filtered properly, and again it will supply to the machining zone in between the tool and workpiece in order to gain the insulation quality to a minimum level. Now, the effective flushing of dielectric removes by the products from the gap. Ineffective flushing results in low MRR and poor surface finish. Suppose if you remove the debris in between the tool and workpiece properly, automatically the metal removal rate will be increases. Otherwise, what will happen? The metal we are going to get the low metal removal rate and poor surface finish also. The effective flushing may be increased MRR as much as by a factor of 10 or so. The poor flushing ends up with a stagnation of dielectric and building up machining residues which apart from low MRR and lead to the short circuit and arcs. Suppose if you didn't remove the debris which are present in the dielectric fluid, then automatically the main drawbacks will come into the pictures like low metal removal rate, and it leads to the short circuit and arcs. So if you want to overcome the problems of short circuits and arcs and low metal removal rate, the machining zone will be properly flushed away, and whatever the debris present in the dielectric fluid, it should be cleaned properly before supplying to the machining zone. A good flushing system is the one that shoots the dielectric to the place where the sparking occurs. Means we have to supply or we have to flush the dielectric fluid exactly the place where exactly the machining is required or machining is happening. It is felt that adequate flushing in case of blind cavities is difficult. So these are the different methods of flushing of dielectric fluid between the tool and workpiece. The first one A is the suction through the dielectric fluid. Means it moves the dielectric fluid from bottom to top. Means from the reservoir on the surface of the workpiece, it moves in the down upward direction through the hole which is created inside the workpiece. The second one is the dielectric fluid will be supplied from the sides of the workpiece and it is directly flows the place in between the tool and workpiece, and it will be come down in the downward direction, that is suction through the workpiece. And third one is the pressure through the electrode. So supplying from the workpiece but flushing away in the upward direction, the flushing in the upward direction. And D is the pressure through the workpiece. Means whatever the dielectric fluid is present in between tool and workpiece, and it will flushed away from bottom of the workpiece to the top of the workpiece. And this one is the E is the jet flushing. By means of the jet, we are going to supply the dielectric fluid, and because of that one, the whatever the debris are formed or removed from the workpiece, it will be flushed away from this zone. And this one is the periodic cycling of electrodes. This one is the last one, and these are the different methods of flushing the dielectric fluid in between the tool and workpiece. Now coming to the advantages of electrical discharge machining process. The major advantages of this process are any material that are electrically conductive can be machined by electrical discharge machining process. So if the material is a conductive material, then we can machine those materials by means of this electrical discharge machining process. Next, materials, regardless of their hardness, strength, toughness, and microstructure, can be easily machined or cut by EDM process. Means it means that irrespective of, suppose in normal conventional machining process, it is very difficult to cut this mnemonic alloys, super alloys, or some tungsten based alloys, molybdenum based alloys. But whereas in case of electrical discharge machining, if the material is a conductive material, then irrespective of their hardness, irrespective of their strength, irrespective of their toughness, irrespective of their microstructure, without any changing the microstructure, we can cut even complicated shapes also by this electrical discharge machining process. Next, the tool and workpiece are free from the cutting forces. In conventional machining process, because of this direct contact between the tool and the workpiece, very large amount of cutting force will be applied on the surface of the workpiece, and because of that one, friction will be developed. Because of that friction, the workpiece properties or microstructure may change. But here there is no direct contact between the tool and workpiece, and here no cutting forces will be developed, and because of that one, no bursts or no cutting forces will be generated in electrical discharge machining process. And edge machining and sharp corners are possible in case of the EDM process. See, the edge machining and sharp corners are very much difficult to get in a conventional machining process, but those properties or those points can also be reached by means of this electrical discharge machining process. The tool making is easier as it can be made from the softer and easily formable materials like copper, brass, and graphite. See, in conventional machining process, the tool materials are like high-speed steel, tungsten-based steel tools, molybdenum-based tools, or ceramic tools, composite tools. It is somewhat difficult to prepare as per our requirement. But whereas in case of the electrical discharge machining is, the tool need not be harder than the workpiece materials. As part of that one, we are going to use this copper, brass, and graphite as the tool materials, and machining of those materials are also very easy, so that you can easily manufacture the tools at any convenient size and shape. This process produces good surface finish, accuracy, and repeatability. Means whatever the components or whatever the products produced in this electrical discharge machining process are getting very good surface finish, and they are getting very good accuracy. And the same accuracy and surface finish we're going to get in all the components without any deviation, without any problem. Then hardened workpieces can also be machined, since the deformation caused by it does not affect the final dimensions. So in case of the conventional machining process, because of the direct contact between the tool and workpiece, a large amount of force will be developed. Because of that one, the dimensions of the components may change sometimes. But in case of the this electrical discharge machining process, there is no point to bother about this changing dimensions of the workpiece. And the components which are produced in this electrical discharge machining process are burr free, means no burrs are formed during this electrical discharge machining process. Now coming to the limitations of this electrical discharge machining process, material removal rates are low. See, when comparison to the conventional machining process, here very small amount of material is removed from the each spark, so that it is going to take more amount of time. Very metal removal rate is low, and the making process is economically only for the hard and difficult to machine materials. So whatever the components are, wherever it's required to machine a hard components like a tungsten, molybdenum, titanium, high-speed steel, nickel-based tools, nickel-based steels, like a hard material, high strength and high temperature resistance materials. Those materials are very much difficult to cut by normal machining process.